20th. A heating element using nichrome connected to a 230 volt supply draws an initial current of 3.2 ampere which settles after a few seconds to a steady value of 2.8 ampere. What is the steady temperature of the heating element if the room temperature is 27 degrees Celsius and the temperature coefficient of resistance of the nichrome is 1.70 into 10 to the power minus 4 per degree Celsius. So in this case, this T1 is 27 degrees Celsius and the current I1 is 3.2 ampere. The voltage is 230 volt. When temperature is T2, that we have to find, that time the current I2 is 2.8 ampere and the temperature coefficient of resistance alpha is 1.70 into 10 to the power minus 4 per degree Celsius. We have to find this T2. We know this RT equals to R0 into 1 plus alpha delta T. So RT will be this, according to, we know I equals to V by R. So we can find R equals to V by I. So RT will be 230 divided by 2.8 equals to R0. We can take up the room temperature. This is 230 divided by 3.2 and 1 plus alpha is 1.70 into 10 to the power minus 4 delta T. So this 230 will get cancelled out. This 3.2 divided by 2.8 will be equals to 1 plus 1.70 into 10 to the power minus 4 delta T. So here it is 8 and here 7. So 8 by 7 minus 1 equals to 1.7 into 10 to the power minus 4 delta T. So it is delta T will be equals to 1 by 7 into 1 upon 1.7 into 10 to the power minus 4. That is equals to 10 to the power 4 divided by 1.9. And that comes to be, delta T comes to be 840.3 degree Celsius. Now delta T equals to T2 minus T1. So T2 equals to delta T plus T1, that is 840.3 plus 27, that is 867.3 degree Celsius is the correct answer. Show that the least possible distance between an object and its real image is in a convex lens is 4f, where f is the focal length of the lens. So in case of convex lens, you have seen, if it is a lens, this is f, this is 2f, here it is f, and here it is again 2f. If you place an object at 2f, then the image is formed at 2f. So the distance between these two is 2f, that is 4f. This is the distance. When you move it towards here, then the image shifts beyond 2f, and ultimately when you bring it to f, then it goes to infinity. That means that time the d becomes infinity. That means when you bring it near to this, the distance will increase more than 2f and ultimately it will go to infinity. So this way, conceptually, it is very clear that the minimum distance is 4f. But numerically also we will just prove it. So I will just do it. We can have distance between the object and the image is d. So if it is here, then u, it is not 2f, it may be anywhere. And if it is v, then it is d minus u. So according to Lenz's formula, 1 by f equals to 1 by v minus 1 by u. That means 1 by v is d minus u, and minus 1 by u is minus 1, so it will become 1 by f equals to 1 by d minus u plus 1 by u. That is, u into d minus u is the LCM, and it will be u plus d minus u. You will get cancelled out. So you have fd equals to ud minus u square. So you will get u square minus ud plus fd equals to 0. So we can solve for u as plus d plus minus under root d square minus 4fd upon 2. For real roots of u, this d square minus 4fd should always greater than or equal to 0. That means d minus 4f should always greater than or equal to 0. So that means this d should always greater than or equal to 4f. That means d may be maximum anything, but the least value is 4f, greater and equal to. So equal to will be the least one, and more than that will be the infinity, as I have already explained it. So here mathematically also it has been proved. 21 or part. In an astronomical telescope, in normal adjustment, a straight black line of length capital L is drawn on the objective lens. The eyepiece forms a real image of this line whose length is L. What is the angular magnification of the telescope? Here, the normal adjustment means the image is formed at infinity, and the length of the telescope is always FO plus FE, and the magnifying power of the telescope is FO by FE. That means this is the objective lens. So here L is printed on the lens, this one, and the image of this L is formed by this eye lens of length small l. And it is normal adjustment. That means this total length is FO plus FE, and magnification of the telescope is FO by FE. The magnification of the telescope is FO by FE. For eye lens, UE is minus of FO plus FE. Just see, L is marred on this lens and it is at a distance of FO plus FE. So VE we can calculate with the help of the lens formula for eye lens. So 1 by FE equals to 1 by VE minus 1 by UE. That is 1 by VE plus 1 by FO plus FE. So 1 by VE will be equals to 1 by FE minus 1 by FO plus FE, which is equal to FE into FO plus FE, and here it will be FO plus Fe minus Fe. So Fe will get cancelled out. So VE will be equals to Fe into Fo plus Fe divided by Fo. Now the magnification for eye lens will be always VE by UE. That VE is Fe into Fo plus Fe divided by Fo, and that whole divided by UE, and UE is Fo plus Fe. So this will cancel out. So this comes Fe by Fo, where it is also equal to VE by UE. That means the I upon O, the magnification is size of the image upon size of the object also. So that I can write L upon capital L. So this is the ME, or you can say Fe by. So that implies Fo by Fe equals to L by L. Therefore, capital M, that means magnification of the telescope. This is the magnification of the eye lens, and this is the magnification of the telescope. That is Fo by Fe, which is nothing but capital L by small l. So this is the correct answer.